default.
No, that's okay. That's sorted. Okay, so I think we're ready. So recall that a group is a set G with a specified element E in G, and a binary operation let me write it as star for now. This is like a function from the Cartesian product of G with itself into G, such that first we wanted the specified element E would be neutral with respect to the binary operation. So for any x in G, E star x is equal to E to x and is also equal to x star E. 2, we want associativity. So for any x, y, and z in G, x star y star z is equal to x star y star z. And 3, for any x in G, there exists an element which we denote as x minus 1, such that x star x minus 1 is equal to E and is also equal to x minus 1 star x. Okay, so but as a notation convention, we usually replace star either by dot when we talk about structures with multiplication, or we can denote star by plus when we talk about structures that have a natural addition in them, and correspondingly we denote the unit element in the plus case. We denote the unit element as 0, and the unit or the neutral element in the multiplication case we denote as 1. This is the convention, and in fact, I don't want to drag the notation star. I just wanted to stress the fact that this is kind of a vanilla, a binary operation that you could think of as multiplication and as addition, depending on the context. But when nothing is known on G, we use G dot 1. Now, a group G is abelian if for any x and y in G, x, y is equal to yx. Okay? And this abelian groups, or also sometimes called commutative, are particular kind of groups that we will focus mostly on in the course, but I think it's a good pedagogic approach to not dive straight into abelian groups and do the theory for general, possibly non-abelian groups. As a notation, in that case, we write a G in additive notation. I mean, again, if we only know that G is an abelian group, then we naturally write the binary operation as addition. And this is a convention. Of course, we could have used multiplication still in this case. If we just take the analogy from numbers, then both multiplication and addition are commutative operations. So there is no apparent reason to prefer one over the other. But of course, we may run into an abelian group that whose binary operation is naturally multiplication. An example for it let n be some natural number, and G as a set is the set of nth roots of unity over the complex numbers. This, I remind you, this is the set of solutions to the equation. So this is all x in C, or maybe z in C, such that z to the n is equal to 1. Or in other words, it's the set of roots of the polynomial z to the n minus 1. And we saw that this set comes naturally with a group structure where you take the binary operation to be multiplication of complex numbers. And the unit element is the complex number 1, which is 1 plus 0i. So this is indeed a group, and in fact, an abelian group. But it's natural to write this abelian group as in a multiplicative notation, okay? Because we do multiplication of complex numbers. Let me give you an example of another group. So let n be a natural number. The symmetric group on n letters this is also called a permutation group. Is the set Sn is the set of all functions from n, that is n is the set of numbers 1 up to n, to itself, such that a sigma is bijective. Okay, let me, you know what, let me just write it again. So for a natural number n, I write this bracket n to be the set of numbers 1 up to n, and the symmetric group on n letters is the set Sn, the set of all functions sigma from n to n, such that sigma is bijective. And on this set, I have a natural operation. If sigma and tau are two elements in Sn, that is, two functions from n to n, then sigma operation tau, maybe we do it like this, star tau, is defined to be sigma composed with tau. Okay? And I have to say something, because if I just compose two functions, I mean, I get a function, but I need to know that I got a bijective function. Note that sigma composed tau is bijective as a composition of such. Okay, we had a proposition when we talked about injective, surjective, and bijective functions, that if you compose two injective functions, you get an injective function. And if you compose two surjective functions, you get a surjective function. So the same is true for, sorry, I have to take this. Hello? Sorry. So So we get that we have a binary operation. The identity map, identity function, id n, from n to n, it satisfies sigma composed identity is equal to sigma, which is equal to identity composed sigma for any sigma in Sn. In fact, for any sigma from n to n, this equation would be true. So we have a binary operation, and we have a candidate for a neutral element. And what we need to check, well, we need to check associativity. But associativity of the binary operation comes from associativity of composition. Okay? Star, or rather circle, is associative since a composition of functions is associative. And the last axiom we need to check is the axiom of inverse. We need an existence of inverse for every function. But if sigma is some element in Sn, then since sigma is bijective, it has an inverse as a function. And this inverse is typically denoted as sigma minus 1. This is again a function from n to n. So this is a function such that sigma composed sigma minus 1 is the identity function. And sigma minus 1 composed sigma is also the identity function. Here, the domain and the range of the functions is the same, so in both cases we get the identity function on n. So to sum up, Sn together with the binary operation of composition of functions and the neutral element being the identity function on n is a group. And I claim that this group is not abelian. Generally speaking, composition of functions is a non-abelian operation. You can think of it, it's like a function is like an operator, And if I do one operator and then I apply another operator, there's no reason that it's going to be the same as doing it in the opposite order. But so Sn is not an abelian group. So to see why, let me represent a permutation in Sn. I can represent it. For example, let's take n equal 3. But this is true for general n. I represent a permutation by this kind of matrix that says that I map. Where do I map 1? I map 1 into 1, let's say, and I map 2 into 3, and 3 into 2. Okay? And I take tau. This is sigma tau. So this is going to be sigma. And now I take tau to be something that moves 1. So let's say 1 moves to 2, 2 moves to 3, and 3 moves to 1. I think already here, it's not going to be abelian. I mean, the composition of these two, what do you get? I mean, you need to see where 1 goes. So 1, remember, composition, we start from here. I mean, we start from the right-hand side function. So the element 1 first goes to 2, and then the element 2 in sigma goes to 3. So the element 1 eventually goes to 3. The element 2 goes to 3, and then the element 3 goes to 2. So 2 goes to 2. And lastly, 3 goes to 1, and 1 goes to 1, so 3 goes to 1. Now, if I do this in the opposite direction, in the opposite order, so this is tau, right? I do 1, 2, 3, 3, sorry, 2, 3, 1. This is tau. And I do 1, 2, 3, 1, 3, 2. This is sigma. And now you can already see that 1 goes first to 1 and then to 2. So 1 goes to 2. 1 goes to 2. 2 goes to 3, and then 3 goes to 1. So 2 goes to 1. And 3 goes to 2, and 2 goes to 3, so 3 goes to 3. Okay, and this is a different permutation than the composition in the other order. If you want as an exercise, you can in fact do what I did here for general n. And if you want to show that for any n, the permutation group is not an abelian group, you need to find two elements that do not commute, I think you can do the trick I did here for general n.
Right, but do we need to? Because we already found one counterexample for the n equals 2, so.
Oh, but it could be that for n equals 2, it's not abelian, and it could be that above a certain integer, it's an abelian group.
Yeah.
You know, hypothetically.
Yes. Yes. Okay.
So maybe exercise. Prove it for general n. Now we will not do a lot with the permutation group, but at some point later on we will. So I'm not going to spend too much time on it now. For the next example, I need a definition. Already, at the moment, it's a notation. Let FP be the set 0 up to P minus 1.
I'm sorry to interrupt, but before we get carried along, actually, you were saying prove it for n greater than 2. It's actually n greater than 3, because for 2, I think it actually is an abelian.
Yes, you're right. Yeah. For general n greater, I didn't say, but let's say greater than 3. But in fact, we proved it for 3, so you need 4.
Right. Yeah.
So I take a prime P, and I denote by FP the set of elements, integers 0 up to P minus 1, together with two binary operations one of them is plus modulo P, and the other is multiplication modulo P. Okay? Now, I claim this is an important lemma. For any x and y in FP, if you take x plus y to the power of p to the n, so this is for any x, y, and p in FP, and for any natural number n, if you take x plus y to the power of p to the n, you get x to the p to the n plus y to the p to the n.
Right.
Okay, this is like this is called the freshman lemma, because freshmen like to just ignore the brackets and do the operation on each of the terms. So this is the case in which it's actually true. How do we see this? So we are going to prove it by induction. The induction is going to be very, very simple. So we start with the case of n equal 1. I write x plus y to the p according to the binomial formula. So the binomial formula says that you sum over all terms of the form x to the I, y to the p minus I, where the coefficient I goes from 0 up to p, and the coefficient is what is called the binomial coefficient. This is a binomial coefficient. This is, by definition, this is p factorial divided by I factorial times p minus I factorial. This is something that is usually done in school, so I'm not going to prove this formula, but you can prove this formula in induction. I mean, just think of this. It does not depend on the fact that p is prime. You can put instead of p, you can put any integer k. It just think of the if p was 2, then when you do x plus y square, you have xy. I mean, you have a term with xy. The coefficient of xy is 2. And then you have a term x squared, and you have a term y squared. And the coefficient of each of them is 1. Okay? So it's kind of a combinatorial problem to do it for a general integer. But you can count. You do a counting argument, and you get into this binomial formula. Okay, so now p clearly divides p factorial. And p does not divide I factorial times p minus I factorial. This is for I greater than 0 and smaller than p. P always divide p factorial, but p does not divide I factorial times p minus I factorial because p is prime. I mean, I factorial is the product of all numbers up to I. And p minus I factorial is the product of all numbers up to p minus I. If p is prime, then this is a product of numbers that each of them is smaller than p. So none of them divides. I mean, p does not divide either of the factors of the product, so it does not divide the product. Hence, the coefficient p over I is often it's called p choose I. For I bigger than 0 and smaller than p, p divides this coefficient because it divides the numerator and it does not divide the denominator, right? So there could be no cancellation. There is a factor of p in the numerator, and there is no factor of p in the denominator, which implies that x plus y to the p is equal to, I mean, modulo p, or in fp, right? In fp, these coefficients are equal to 0. So x plus y to the p becomes just the first term, that is x to the p, plus the last term, y to the p, right? And the first term, in fact, the first term is when I is equal to 0, so this is just technically, this is, well, okay. This is the last term is x to the p, and the first term is y to the p, right? Okay, so we proved the claim for n equal 1, and now for n equal 2, x plus y to the p square is by definition x plus y to the p, and all that to the p. But by the n equal 1 case, this is equal to x plus y to the p. And applying the n equal 1 case again, I get that this is equal to x to the p plus y to the p. Yeah, I want to. No, I had, sorry. Applying the n equal 1 case once, I get that this is x to the p plus y to the p to the p. But the claim was true for any x and y. So I can apply the n equal 1 case for x to the p and y to the p. So this is x to the p plus y to the p, which is x to the p squared plus y to the p squared. Okay, and for n bigger than 2, this is the same argument. The same repeated application of the n equal 1 case. This is what mathematicians usually call a trivial induction. I mean, formally, if I wanted to write a completely formal proof, I would do it by induction. But you can see that all I'm doing here is just applying the n equal 1 case again and again. Any questions on this lemma, the freshman lemma?
Isn't it was that the first row, like applying the, yeah, we know that this POI is 0, then we are inserting it into a formula. And
So if I know that the coefficient here, I mean, x plus y to the p is equal by, I mean, with the binomial formula to this sum in blue. Now, if I know that the coefficients in this sum almost all the coefficients are 0, modulo P.
Yeah, but all of them?
Not all of them. So which one? The ones, so this is for any I that is not 0 and not P. That is, the first coefficient is not 0, and the last coefficient is not 0. If you think of it, the first coefficient, when I is equal to 0, this is P over I. What is P over I? It's 1, because this is, I mean, P over 0 is P factorial divided by 0 factorial, which is 1, times P factorial. Okay, so the coefficient, the first coefficient is 1, and also the last coefficient is 1. Now, what is the monomial corresponding to the first coefficient? That is, what is this x and y term when I is equal to 0? When I is equal to 0, this is x to the 0 times y to the, here this is not p minus 1, this is p minus I. Okay? So this is, the term is y to the p. And the last one is going to be x to the p. Okay, so I get that x plus y to the p is x to the p plus y to the p. Any other questions? Maybe from online? Okay, so with this lemma we can do something nice. This is called a Fermat a little theorem. And Fermat little theorem says that if P is a prime and A is some number between 1 and P minus 1, then A to the P minus 1, well, let me do it like this. A to the P is equal to A. Okay, so proof.
Oh, right, yeah.
So by induction on A. If A is equal to 1, this is clear. Suppose A to the P is equal to A. And now we do the A plus 1 case. Then A plus 1 to the P is equal to A to the P plus 1 to the P by the freshman lemma. And by the induction hypothesis, this is equal to A plus 1. Because by induction hypothesis, A to the P is equal to A. So I get that A plus 1 to the P is equal to A plus 1. Okay, that's the whole proof.
And question.
Yeah.
I thought of a different proof, but I don't think it works. What if we say a minus? No, wait, it doesn't work. Okay, forget it then. Sorry.
Okay, so using Fermat a little theorem, we get into this important example. Let FP star be FP with the zero element removed. And only multiplication modulo P. Okay, so now I take only the elements 1 up to P minus 1. And I only consider multiplication modulo P, no addition. Then FP star together with multiplication and the element 1 is a group. In fact, an abelian group. So unitary and associativity axioms are immediate. I mean, obviously, 1 is a neutral element with respect to multiplication modulo P. And also, multiplication modulo P is an associative operation. Whatever you put into it, you can move the brackets either from the beginning or to the end. So, neutral element plus associativity axioms are immediate. What is what requires some argument is the inverse axiom. So for the inverse, let A be an element in FP star, i.e., A is a number between 1 and P minus 1. Then by Fermat, A to the P is equal to A. Which means that A times A to the P minus 1 minus 1 is equal to 0 modulo P, right? This is modulo P. Which is equivalent, I mean, two numbers that are equal to 0 must satisfy that one of them is equal to 0. So A is not equal to 0. So it must be that A to the P minus 1 is equal to 0 modulo P. Which means that A to the P minus 1 is equal to 1 modulo P. which is the same as saying that A times A to the P minus 2 is equal to 1 modulo P. So the inverse of A is A to the P minus 2. Okay, as desired. So you see, we have a collection of examples of groups. Some of them, I mean, most of the groups we talked about are abelian, but the exception was the symmetric group. And some abelian groups may come naturally with multiplication. Some the binary operation can be naturally viewed as addition. And if, as I said earlier, by convention, if we don't know anything about the binary operation, but we only know that it is abelian, we write it as a plus.
Oh, if we don't know that.
If we don't know, yeah.
Okay.
If we know the details, I mean, this, you know, if we have it like here, FP star, we know the binary operation is a multiplication modulo P. So we're not going to write it as addition. This is going to cause a lot of confusion. Last thing before the break. Let G and H be groups. The group G times H is, as a set, it is just a Cartesian product of G and H. This is all X, comma Y, such that X is in G and Y is in H. And I need to tell you what is the binary operation. We define star. This needs to be a binary operation from G times H to itself. So this is, it takes as an input 2 pairs in G times H. So I take, let's say, X comma Y, and I want to multiply it by X prime comma Y prime. So I do the obvious thing. This is going to be defined as X times, maybe I do it like this. G comes with operation star sub G, and a neutral element 1 sub G, and H has a similar notation. And then in the first coordinate, I do multiplication in G. And in the second coordinate, I do multiplication in H. So sorry, this needs to be X. Maybe I write it like this. Is X multiplication in G, X prime. Y multiplication in H, Y prime. Then a exercise maybe. This set G times H with the operation dot and the unit element or the neutral element 1G, comma 1H is a group. Okay, it's very easy to check. All axioms follow essentially because they are valid in both G and H. Any questions before we take a break?
Yes, is it a group or an abelian group?
If this you can add to the exercise, if G and H are both abelian, then it is going to be an abelian group.
Yeah.
But if one of them is not abelian, then it's not going to be an abelian.
Right.
Okay, so let's break here and see you in 10 minutes.
Yeah.
Okay. Let me just remark something about this step in blue here. I mean, in the assuming we know by Fermat that a to the p is equal to a, then we can definitely write it as a times a to the p minus 1 equal to 0, modulo p. But how do we know that if the multiplication is 0 modulo p, then the right-hand side factor of the multiplication has to be 0 modulo p. If it was a 0 on the nose, then of course we know that two integers that multiply into 0, one of them has to be 0. But this is 0 modulo p. So, but we know that a is smaller than p minus 1 and bigger than 1. So if the product is equal to 0 modulo p, it means that p divides the product. If p divides a product, if any number divides a product, it has to divide, well, actually, if the number is prime, it has to divide either the first factor of the product or the second factor of the product. And since a is smaller than p minus 1, it means that p cannot divide a. So I will add here, p does not divide a, hence it has to divide a to the p minus 1. Okay, so this is just to be more complete on the proof. But we will use, so if you notice what we have here, this fp, the set of numbers 0 up to p minus 1 with addition modulo p and multiplication modulo p, it is what is called the field. That is, we have a structure of a abelian group with respect to multiplication, and a abelian group with respect to addition, with the neutral element being 0. And if we remove 0, we have an abelian group structure with a multiplication and neutral element being 1. And in a field, we will get to it later on, but in a field you have an additional axiom that requires compatibility of addition and multiplication. This is called the distributivity. So you want that x times y plus z is equal to x times y plus x times z. But this is also true for addition and multiplication modulo p. So fp is a field with p elements.
So, yeah, what's the confusion is, so the group over this prime field does not include 0, but this proof over prime field, so because they like assume the result of multiplication is 0.
So remember that in a group, we really require that every element has an inverse. So if I take fp is all the numbers 0 up to p minus 1. And I take the operation of multiplication modulo p. If I take all fp, that is, I include 0, then not every element will have an inverse.
Yeah. I get like how I understand this is that so this proof is over fp. So these operations in this proof are over fp, but like multiplication of in the group operation is something different. It's different multiplication.
No, I mean in from the set FP, let me write it here, we take the set 0, 1 up to P minus 1. This I called FP. And I call well, FP star is the set 1 up to P minus 1. So here, if I add addition modulo P, and I take the neutral element to be 0, then this is a group. And here, I can take multiplication modulo P and neutral element being 1, and this is again a group. Both are abelian groups. And so, okay, we will get to the definition of a field later on, but this will be something that has both addition and multiplication, and addition makes it an abelian group, and multiplication, if you remove the 0, makes it another abelian group. So it's like two compatible abelian group structures. Okay. So let G, and I remind you, for a general group, we write G multiplication and 1 a subset H in G is called a subgroup if the following conditions are met. One is that the neutral element has to be in the candidate to be a subgroup. 2, for any x and y in H, x times y is also in H. In a priori, all we know is that x times y is in G. But the condition for a subgroup requires that you multiply any two elements in the subset, it remains an element in the subset. And 3, for any x in H, the inverse of x is also in H. In other words, a subset H in G is a subgroup if and only if, in fact, H is a group with respect to the operation from G. The binary operation star from G. Okay? Now, we saw a few examples. So let's check this notion with the examples we had. So I take the complex numbers and I remove 0, and I consider it as a group with the multiplication of complex numbers and the unit element or the neutral element being the complex number 1, which is 1 plus 0i. This is a group. This you can call G. And within this group, I have H, the group of nth roots of unity, mu n of C. This, I remind you, this is the set of all complex numbers Z, such that Z to the n is equal to 1. And here again, I take multiplication and a unit element. I should remark the notation. If H is indeed a subgroup of G, we write H smaller or equal to G instead of just inclusion. Right? We write a smaller or equal to G to denote that H is a subgroup of G. So here, H is a subgroup of G. Second example, G is the group of integers modulo 10 with addition, right? And H is the subgroup. Well, it's going to be a subgroup, but it's as a subset, it's the set of the elements 0 and 5. Zero and 5 is indeed a subgroup of integers modulo 10. Because if I add two elements in the set H, I get, the only non-trivial thing that I could do is to add 5 plus 5. 5 plus 5 is 0 modulo 10. So I stay with within the subset H. If I want, what is the inverse of 5 in Z modulo 10? It's 5. So the inverse of 5 is still in set. And yeah, that's it, right? And the neutral element 0 is of course in the subset.
But the neutral element has inverse of itself. Inverse of the neutral element is itself.
Yes.
But this is also true for 5.
Yes.
Yeah. Is it okay?
Yeah, that's fine. All we care about, we want that the third, for example, the third condition will be met. The third condition means for any x in H, the inverse of x is in H. Again, here, the inverse, I forgot to say it in the notational convention, but when we use addition, the notation for the inverse is instead of to the power of -1, the notation for the inverse is minus the element. Because the inverse needs to be inverse with respect to the operation. So the inverse of 0 is 0, the inverse of 5 is 5, and it follows that H is a subgroup of G. However, if I take the set H prime to be a 0, 2, for example, then it is not a subgroup. Because, well, for many reasons. But one reason would be that if you take 2 plus 2, then you get 4. And 4 is not in the set. So you need to, I mean, a subgroup needs to be closed under the operation of the ambient group. So I write it like this, not a subgroup of G. Okay. The set, consider G to be the integers, and H is the subset 0 up to n minus 1. Of course, when I say G is the integers, I really mean G of it being the integers with addition and the 0 element. And I pick some natural number n. This is what we refer to as Z modulo n. But this is not a subgroup of Z. Z modulo n as a set is not a subgroup of G. So you see, each of them independently is a group, but they are not, I mean, the smaller one is not a subgroup of the bigger one. And the reason is that the operation, I mean, the operations that make Z modulo n a group, the binary operation is radically different than the binary operation that makes a G as a group. I mean, addition modulo n is not the same as addition. Now, on the other hand, if I take G to be the integers, I take a natural number n, so fix a natural number n, and consider H to be, this is denoted as nz. This is all the multiples of n. So this is n times x, where x is an integer. Then H is indeed a subgroup of G. Why? If n times x and n times y are two elements in H, then nx plus ny is equal to n times x plus y. Hence, it belongs to, it is a multiple of n again. So the set H is closed under the operation of the ambient group G. Obviously, the neutral element 0 is equal to n times 0, so it belongs to nz. And now I want to see that the inverse stays in the I mean the inverse of an element in H is again an element in H. But this is easy. If nx is an element in nz, then n times minus x, which is an element in z, sorry, in nz, is the inverse. Satisfy nx plus n times minus x equal to 0. Okay, so nz, all the multiples of a given integer is a subgroup of the integers. We talked about the product of two groups. Let G and H be any groups, any two groups, and consider, well, then I claim G times H, or the group, has two canonical subgroups. One, so I remind you, G times H is the set of elements x, y, such that x is in G and y is in H. Within this set, I can take G Cartesian product with the set that has one element being the neutral element of H. This Cartesian product is simply the set of all pairs x, comma 1h, where x is in G. And obviously, this is a subset of the whole Cartesian product, G times H. And on the other hand, I can take the neutral element of G. I take the set with one element being the neutral element of G, and I take the Cartesian product with H. This is specifically, this is the set of all pairs 1G, comma Y, where Y is in H. And again, this is a subset of G times H. And I claim that these two subsets are in fact subgroups. Both are subgroups. Yeah, I leave it as an exercise.
What is the law or what is the operation for this?
If I claim that they are subgroups, then the operation has to be induced from the operation of the ambient of the big group.
Right, that's my question. What is
The operation is coordinate-wise. You take x y times x prime y prime. You do x times x prime, y times y prime. At the times, in each coordinate, you do the operation in the relevant group. The first coordinate is the operation in G, and the second in H. Okay, so let me perform a main construction that we will consider in groups. So let G be a group. And X an element in G. For a subgroup H in G, the left coset of H with respect to X is the set XH. This is all the products, all the elements of the form X times H, where H is in H. Sometimes this is denoted like X dot H. So what we do here with cosets, we kind of abuse notation, and we use the binary operation dot to apply to be an operation between an element and a subset. Okay, this is just for getting notation to be intuitively understandable. What it means is that I take all the products. I take X and I take all the product of X with elements in H. Now observe just a few, simple things. I mean, if I take EH, the coset EH, not E, 1H, then this is simply H, right? I take 1 times every element in H. This one is the one in G. I take the coset of 1, it's simply H.
So I have a terminology question. You say the left coset. Oh, so left coset of H with respect to X. Okay, yeah.
Yeah.
Makes sense.
Okay, of course, I could have done a right coset. Right coset would be HX. It's all the products, H times X. If we don't assume that G is abelian, then left cosets could be different than right cosets. But we are very soon we are going to assume that G is abelian, and then it's not going to matter. So we might as well just choose one, either left or right, and stick to it. And if X, so this, the first observation is this. The second, if X is in H, then the coset of X H is again H. Right? Why? You take XH, I mean, X has an inverse in H. X is in H, then the inverse of X, X minus 1, has to be in H because H is a subgroup. So the neutral element 1, which can be written as X times X minus 1, it has to be in XH. Right? Because it is X times an element in H. You see this, Andre? Okay, so 1 is an element in XH. And now, given some Y in H, so I guess to show equality of sets, I need to show inclusion of both sides. So if T is equal to XH, an element in XH, then clearly T belongs to H because it is a product of two elements in H. Okay, so this means that XH is contained in H. And if H is an element in H, then I can write, I want to write H as, then I can write H as X times X minus 1 times H. And this is an element in XH because it is a product of X and some other element in H. Why is this other element in H? X minus 1 is in H because X is in H and H is a subgroup. Little h is assumed to be an element in H. And since H is a subgroup, product of two elements in H are in H. So I can write a small h as X times another element in H. And hence, small h is in fact an element of the coset, the left coset XH. This means I started with a general element in H. This means that H is contained in XH, which of course means that H is equal to XH. Okay, so it's a funny operation. I mean, kind of swallows everything that you put into it that is already in the cycle. Example. I take G to be the integers and H to be integers which are multiple of a given integer. Here again, I fix I fix N. Okay, so clearly H is a subgroup of G. This is what we talked about in the examples. What is the coset? So remember the way I wrote left cosets, I wrote it with multiplication because for a general, our notational convention for a general group is that we use multiplication as the binary operation. But here, in this example, the binary operation is plus. So for x in G, the left coset is written as x plus nz, right? So instead of product, I put plus, and instead of age, I put nz. So x plus nz, if you think of it, it's just the set of all integers of the form x plus n a for a and z. Note. So I take, for example, 1 plus nz. This is a coset. I claim that it's the same coset, it's the same set as n plus 1 plus nz. And it's the same as 2n plus 1 plus nz. And so on. Right? You see why? Because let me do the first equality, and then you get the principle. 1 plus nz, or let me do n plus 1 plus nz is the set of numbers of the form n plus 1 plus na, where a is in z. But I can write it as the set of numbers of the form 1 plus n times a plus 1, where a is in z. And this is equal to the set of numbers of the form 1 plus n, let's call it a prime, where a prime is in z. Right? I mean, if a is allowed to vary over all integers, then a plus 1 also varies over all integers. And this last set is what we call 1 plus nz. Okay? So you see, we have a lot of different cosets that are equal. In fact, how many distinct cosets should we expect in this case? We fix an n. We look at the group of integers and the subgroup nz. How many distinct cosets should we expect to have? I mean, how many x plus nz? How many different sets will we obtain when we do x plus nz, where x runs over all z?
And
It should be n, right? So I don't want to prove it now because we are getting close to the end. But let me put it as put something as an observation. What I want to know, I mean, in order to realize how many distinct cosets I have, I want to know when x plus nz is equal as a set to y plus nz. I want to have a condition depending only on x and y that will guarantee me that if this condition is met, then these two cosets are equal.
they have the same remainder in the division by n.
Yes. I claim that these two cosets are equal if and only if x is equal to y modulo n. And the way to see it is as follows. I mean, if x is equal to y modulo n, then x minus y, or rather, yeah, I guess I could do x x minus y is equal to na, i.e. x is equal to y plus na. Maybe instead of a, I put t. But then, when I do y plus nz, this is the set of all y plus na, a in z, then I might as well write, oh, sorry, when I do x plus nz, this is x plus na, where a is in z, but x is equal to y plus nt. So I can write it as y plus nt plus na, where a runs over all elements in Z. And this is equal to y plus n t plus a, where a varies over all Z. But t is fixed. So if a varies over all t, so over all z, then a plus t also varies over all z. So this is y plus n a prime, where a prime is allowed to vary over all z. And this is by definition the set y plus nz. Conversely, if I know that x plus nz is equal to y plus nz, then for a given element in Z, x plus NA, which is an element in x plus NZ, it must be an element in y plus NZ. So there exists an element A prime in Z such that x plus NA is equal to y plus NA prime. But this means that x minus y is equal to n a prime minus a, which is the same as saying that x minus y is equal to 0 modulo n. Okay, so you see, we know actually when two cosets here are equal. They are equal if x and y are equal modulo n. All right. I guess it's good to stop here. Any questions about what we did today? It was I think it was quite a lot of new things.
Yeah, I would have a question, but we can talk about this next time. What would be an example of a coset that is not using number theory? I mean, like modular arithmetic.
Well, a lot. I mean, think of the group of n roots of unity.
Okay. Yeah.
Right? This is a subgroup of the complex numbers.
Right.
So take any complex number,
Yeah.
and look at the coset of the complex number with, I mean, of the subgroup of n roots of unity
Mhm.
with respect to this complex number.
Right. But that's the same thing, right? It's like you have n roots of unity,
Yeah,
so-
okay. I mean, eventually, yes, because I mean, n roots of unity is isomorphic to, but it's not. I mean, you know, one is addition modulo n, one is multiplication of complex numbers.
Right, and okay, so one example would be, because this is also isomorphic to rotations somehow, like at least it rotates along the.
I don't want to answer that too much because we didn't talk about isomorphism,
Okay.
right? But we will definitely see many examples of cosets, and eventually, I mean, what we will do with these cosets is we will define quotient groups.
Okay. Right.
So okay, but I don't want to jump ahead to that.
Maybe from the chats.
Yeah. I was hoping someone would ask anything today in the chat. Nazar, Yevgeny, Craig, you have maybe requests for next time, because I didn't hear any question from you today. Yeah, Nazar, are you trying to speak? Okay. Okay, so it's good, but it would be good. I would be happy to hear questions that you might have generally in the sessions. So feel invited. And I guess otherwise we meet again next week. Right. Bye-bye.